Hello. In this presentation, James and myself will be breaking down our anchor paper, which presents a novel solution to dealing with packet loss in TCP. The paper provides a particularly interesting approach related to the mechatronics field by integrating a classifier trained using supervised learning into a network protocol. This end solution attempts to meet a demand to make TCP operate more efficiently with wireless networks.
TCP was introduced in 1983 and is now widely used in most current internet applications. TCP provides a protocol for two hosts to establish a connection and to reliably exchange streams of data. It achieves this by reducing the transmission rate when a packet loss is detected. However, packet losses can be caused by either congestion in the network or by link errors. Since TCP has no way of telling them apart, it treats any packet loss as a congestion and reduces the transmission rate. This is a suboptimal solution, and the throughput of data could be improved. But first we must be able to distinguish between packet losses due to congestion and packet losses due to link errors. Our anchor paper aims to accomplish this by using supervised learning and prevent TCP from reducing the window size. If it is successful, it could result in a higher throughput of data, especially in wireless networks when utilizing TCP. TCP has become a popular protocol due to its ability to provide a reliable method of data transfer by guaranteeing that the data will be delivered in the same order they were sent. However, several studies have proved that TCP is poorly optimized over wireless links. It is well documented that TCP was created when wired links were the standard, and the protocol's method of dealing with link errors are outdated. When TCP was created, wireless networks were largely unpopular, and so TCP was mainly optimized for more traditional networks with wired links and stationary hosts. This meant that most packet losses experienced by TCP at the time were caused by congestion and not link errors. Now that wireless links are becoming abundant, link errors occur more often due to noise on the wireless channel. Since TCP has no way of distinguishing between congestion and link errors, it treats both as a congestion and reduces the transmission rate. In the case of a packet loss caused by a link error, it is unreasonable for a transmission rate to be reduced, as there is no congestion on the network. Recently, several methods have been proposed to combat this loss of throughput. These methods can be grouped into two approaches: methods which hide any non-congestion related losses from the TCP, or methods that make the TCP aware that the packet loss is of a non-congestion type. By hiding the non-congestion packet losses from the TCP sender, it will require no changes to the existing TCP protocol. These methods have used mechanisms such as local transmission and split TCP connections. Local transmission uses the approach of hiding the link errors from the TCP. When a packet loss is detected caused by link errors, the packet is retransmitted in the link layer. The split TCP approach utilizes two separate reliable connections, one between a sender and the base station, and one between the receiver and the base station. The protocol used at the base station can be tuned to wireless links and therefore improve the data throughput. This approach again deals with the link errors before it reaches the TCP sender. Either methods of hiding the non-congestion related packet losses or revealing them to the TCP sender require that the different types of packet losses to be distinguished. Therefore, this topic of distinguishing the different types of losses has gained significant research and many approaches have been proposed. One of the earlier methods of detecting a link error loss is to use a delay threshold. When a packet loss is detected, the algorithms would compare the current round-trip delay with a calculated delay threshold. If it is less than the threshold value, the algorithm concludes that the network is being underutilized and the reduced throughput is caused by a non-congestion loss. It can therefore go on and rapidly retransmit the packet. These methods needed to be extremely conservative and proved to be less than ideal. This method of using round-time trip is utilized in TCP approaches called New Reno and Westwood. Later implementations proposed the idea to classify the causes of packet loss using a combination of several indicators instead of just one. Many methods were explored to characterize the network conditions that would result in a certain type of packet loss. However, due to the large number of random external factors, such as user behavior, current topologies, research quickly turned to automatic learning techniques to gather large ranges of data to classify the packet losses. Since these algorithms have such a large range of classified indicators to cross-reference with, they can be much more aggressive and therefore achieve higher throughput of data. As of recently, most research have only proposed the different types of automatic learning techniques to create a classifier. Most only propose that we use the approach to hide the link errors from the TCP sender rather than letting it know. Our anchor paper, on the other hand, first applies a number of supervised learning techniques to gain an understanding of the best one. It then employs the highest performing classifier and extends the TCP protocol to be able to identify the packet loss and deal with it. This anchor paper was one of the first to apply the idea of supervised learning and perform experiments to acquire real-world results.
This anchor paper has explored a number of key concepts and outcomes, providing a significant contribution to the field of networks. As previously discussed, the primary aim of the anchor paper is to develop a new enhanced TCP implementation which features a packet loss type classifier. The protocol is novel in the sense that whenever packet loss is detected due to a triple duplicate, the classification model will be queried for its actual source. If it's by congestion, TCP acts normally and divides the window size by 2. However, if it's classified to be due to a link error, TCP doesn't reduce the window size. Based on this ultimate aim, there are two primary outcomes that are presented in this paper. The first is to determine which supervising learning algorithm results in the best classifier for enhanced TCP. The second outcome is to test performance of the enhanced TCP in regards to parameters such as throughput and TCP friendliness. To satisfy the first outcome, 4 algorithms were tested. These were namely decision trees, tree bagging, tree boosting, and neural networks. A classifier was generated using each method on a large database of simulated packet loss scenarios. The classifiers were then tested for performance. The first plot focused on accuracy in response to changing the classifier bias. In addition, a second set of results focused on average computational time required for each classifier to obtain a solution. The end result was that tree boosting was the most accurate, while the decision tree was the fastest. Based on that result, the team decided to run an enhanced TCP instance for both standout cases. To satisfy the second outcome, the enhanced TCP implementations were simulated to evaluate throughput. The first simulation featured a hybrid wired and wireless network with the shown topology. The results are summarized in these two plots. The left displays throughput, while the right displays gain. These are superimposed for a number of enhanced TCPs with differing bias values, in contrast to existing packet loss classifier methods. These include Vino and Neurino. It can be seen from the results that the tree boosting classifier provided the highest throughput. In order to test a purely wireless system, a simulation was also run on an ad hoc case comprised of 50 mobiles. This experiment also showed that the tree boosting classifier provided the highest gain. The second criteria to justify enhanced TCP performance is whether TCP is fair. To test this criteria, an experiment was set up with the scene network topology. The experiment was run for both a wired and wireless case, in which regular TCP was run in competition with the enhanced TCP solutions. We are able to conclude that an enhanced TCP solution is fair if it exhibits similar throughput to the base TCP. By that definition, it can be seen that most of the enhanced TCP setups were fair. On the other hand, the existing alternative Vino was completely unfair. To round off simulation, the gathered results for the performance criteria gain and fairness were summarized in a scatter plot. The plot infers that enhanced TCP with a decision tree-based classifier and the 0.04 bias is highly TCP friendly. On the other hand, if throughput is a higher concern, enhanced TCP with a boosting classifier is an optimal solution.
The key strengths of the paper was that it was able to successfully apply and confirm the idea of using supervised learning techniques to classify the types of losses. It was then able to go further and provide solid evidence along with results from experimentation to prove that classifying the types of losses will improve the throughput of TCP. Some weaknesses of the paper's approach was that it did not take into account losses detected by timeout expiration and were therefore all considered as congestion losses. Secondly, the database that the classifier was based upon were all generated from simulated networks, which may differ from the real-world results.
The anchor paper provides a solid base and out-of-the-box approach to dealing with packet loss in TCP. However, at its core, the concept proposed is fairly rudimentary and could use extension. For example, results would be more convincing if an extended study was undertaken to test full implementation of the model under real traffic. This may provide different results as to which supervised learning method generated the best classifier. Alternatively, it may back up the findings of this paper. In addition, training the packet loss classifier with non-simulated data may yield more accurate results. Another point is that this paper puts a lot of focus into the classification element of the enhanced TCP solution, but not into the response strategy. If packet loss is due to link error, it is simply ignored. Further research may provide a more effective, active solution. In conclusion, the research outcomes demonstrated that supervised learning methods may be used to generate a classifier able to identify the source of packet loss as either due to congestion or link error. Once this distinction is made, packet loss can be dealt with in a more informed manner, leading to an increase in throughput without affecting TCP friendliness. The novel protocol was tested in a number of simulated scenarios with wireless, wired, and hybrid topologies. In each case, the enhanced TCP strategy was able to provide a higher throughput than standard TCP. This was especially the case for wireless topologies, which standard TCP is not well equipped for. Hence, the paper was highly successful in developing a novel protocol for wired and wireless networking.